Okay, let's begin with this. The test that's coming up is 7.6 and all of 8. So your review questions that you need to do to prepare for the test, the stuff that the test will come from. You've got questions number 85, 87, 89, 91, 93, and 95 from 7.6, and then all odds from 8. Okay. And the test will be next week. Let's say next Wednesday for you. What's the date on that? Okay, so the 19th. And the window will do from the 19th through the 23rd for the online class. That's the window for the test. Okay? All right, well, let's get started today. So today we're on a new section. We start dealing with gas laws. I better pray. Let's pray. Father, thank you for today and for the things that we've learned, Lord, and please help us as we learn some new things about gas laws and pressure and volume and how to measure these things and make conversions. And Lord, as we build ultimately into the ideal gas law, help me to understand what I'm talking about and to be clear as I teach. And please give everybody who's here or watching this just grace to understand and to be able to resolve any questions. We pray this in Jesus' name. Amen. All right. You're going to need this. I'm going to hand it to you. If you're online, I'm going to put this up on the website. If I forget, this is right out of the book in the first few pages of chapter 9. But you need these conversions. One conversion that is not on that you need is this one here. So just write it down on that sheet. And it's 1 Newton per meter squared equals 1 kilogram meter per second squared. Need that conversion also. Okay. Let's dive in and see how far we get. I'm going to set a timer so I don't hold us too late. Timer, where we at here? 150? Okay, so gases, they exert a pressure, right? You blow into a balloon, it requires some pressure to blow that balloon up, you let go of it, and the balloon deflates. Why does the balloon deflate?
Outside pressure.
It's pressure from the outside, from the atmosphere is pushing it down. When we talk about any kind of pressure, we're talking about an amount of force over a given area, okay? And so pressure equals F over A. Or how do they have it here? Yeah. Force, pressure equals force over area. So for instance, they give you one here. Calculate the pressure exerted by an elephant. Okay. So an elephant, if an elephant is 14,000 pounds, okay, and it has 4 feet, And each foot consists of roughly, where gives us this? Come on now. .5 square feet. Okay. What is the force that this elephant exerts? So, sorry, what is the pressure that this elephant exerts? So we've got force. We can get to force given our mass. Force equals mass times acceleration. And we've got an area, so we should be able to get to pressure. Catch is, we're in some weird units here, right? But essentially, if I wanted to do this, what I want to get is pressure per foot, right? Per elephant's foot. And so to do that, I take my 14,000. That's pounds per elephant. And then I multiply that by one elephant has 4 feet. And then I multiply that by 14 pounds per, I'm sorry, 1 foot over 200, about 250. One foot at 250 inches squared. And when I run all that math, I get about 14 pounds per square inch. Okay. That doesn't sound nearly so bad as a 14, you know. And one of the things that the book draws attention to is, though an elephant is huge, if you were, because it's that force, mass times acceleration, is exerted over such a large surface area, that you'd be better off standing on an elephant than you would like a little figure skater on her blade. So they give you a calculation for that. Take a 120-pound figure skater, okay, and you multiply that by that skater, figure skater, has 2 blades. Each blade has a surface area of about 2 square inches. Okay. Then that comes out to be 30 pounds per inch squared. So it would hurt worse to stand under her on a blade than it would be the elephant. Just, you know, not intuitive, but there it is. All right. So now, one thing it wants us to know is the SI unit of pressure is the Pascal. It's our SI unit. Okay. And 1 Pascal equals 1 Newton over a meter squared. So a Newton is a unit of force, and 1 Newton equals 1 kilogram per second squared. These conversions are going to become important in the problems that we're going to do very quickly. Okay. There are a number of other conversions that we need to have, and so you've got that chart there, and you guys can look it up. It's page, I don't know what book, but it's there. It's table 9.1. So one of the first things it wants us to do is, you can do this with me? Okay, let's go for it. One of the first things it wants us to do is to convert pressure of 29.2 inches of mercury into First of all, torr. Second of all, oh, I'm sorry. Yeah, torr. Second of all, atmosphere. Third, kilopascals. Fourth, millibars. And fifth, okay, that is it. All right, so we want to get from millimeter or inches of mercury into any of these. I don't care where we're beginning. Our first problem is we're in inches, right? And so we got to get from that into metric, right? So first thing I've got to do is I've got to get from 29.2 inches to,
Pascal.
what's the easiest way to get from inches into metric? A unit we all ought to know. Okay, it's the unit of centimeters to inches. It's 2.54 centimeters per inch. Okay, so times 1 inch, or actually, I gotta go with the opposite of this, times 2.54 centimeters per inch. And so that'll get us into centimeters, okay? Now from centimeters, I need to get to torr, and so I've got a number of ways that I can do that. One is I can get from millimeters to torr, right? So how do I get from centimeters to millimeters?
Divided by 200.
Yeah. How many?
100 or 1,000.
Should be 10, right? 10 millimeters per 10 centimeters per 1 millimeter. I got this backwards. We want centimeters on bottom, we want millimeters on top. There's 10 millimeters per 1 centimeter, right? Okay. So when I do this, you got a calculator? Let me get your calculator if you don't.
Mine is 741.68.
Yeah, so 742, right?
Yeah.
Okay. So this has us in millimeters, right? We skipped one step. That is the number we want, but we got one more thing, and it's that we have a conversion from 1 millimeter to 1 torr, right? So on our chart, we see that 1 torr, at the very bottom, 1 torr equals 1 millimeter of mercury. Okay? And so, what was that number you just gave me? 742.
Yeah.
Okay. All right, so now we want to get to atmosphere. So we're going to do the exact same thing, 29.2 inches times 2.54 centimeters per inch times 10 millimeters per centimeter. And now I want to start working my way towards atmosphere. So I need to look at that chart and find a useful unit to get to atmosphere. And I find that if I have 760 torr, that will give me 1 atmosphere, right? So I can write everything else out the same. Times 1 atmosphere over 760 torr, right? And when I do that, so basically just take my same number divided by 760, and I should get 0.976 atmospheres. That's the correct answer. Good. Now we want to get from atmospheres to kilopascals. So if you look on your chart,
1 atmosphere is 325 Pascal.
I can get from atmospheres to pascals. I'm going to take my 0.976 0.976 atmospheres, right? And I'm going to multiply that by 1 atmosphere. Converts to 101,325 pascals, right? Now I need to get to kilopascals, right? So I need 1 kilopascal is 1,000 Pascal. So I do that math, right? You get
0.0988.
check the math. Something went wrong there.
Not the same answer.
Okay. I'm getting 98.9. Let's try it together one more time. So 0.976 times 101,325 divided by 1,000,
Okay, I think I know what I did wrong.
98.89.
Yeah, I put it 101, and I put a dot.
Oh, and so, gotcha. Okay. Okay. All right, and then now we want to get to millibars. So, how are we going to get to millibars? A bar is exactly equal to 100,000 pascals, right? So let's start back where we were here at 0.976 atmospheres. Okay, and we'll go times 101,325 pascals over 1 atmosphere. Now I know that 100,000 pascals equals 1 bar. And then finally, I want to get from bars to millibars. So I'll have 1 bar over 1,000 millibars. Okay. I get 989.
Yeah, 989.3.
Did that answer?
Yeah.
Okay, very good. All right. Would you like to do another problem like this? Should I roll on?
We can roll on
Okay.
conversions now.
Well, very good. So now I'm just going to have to start looking at some equipment to calculate this and how to work out from there, and we'll get some conceptual understanding of things. We can measure atmospheric pressure, the force exerted by the atmosphere on the Earth's surface, with something called a barometer. A barometer is a glass tube that is closed at one end, filled with a non-volatile, so a liquid that won't evaporate, such as mercury, and then inverted and immersed in a container of that liquid. The atmosphere exerts pressure on the liquid outside the tube, and the column of liquid exerts pressure from inside the tube. And the pressure at the liquid surface is the same inside and outside the tube. The height of the liquid in the tube is therefore a measure of proportional to the pressure exerted by the atmosphere. Here's what it's saying. Okay, I want to make sure you get the concept of it. So you take a tube and you fill it up to here with mercury, or you fill it actually all the way with mercury. Okay. All right. And now you take this tube and you've got some kind of a container over here that's open that also has mercury in it. Okay. I take this container and I turn it upside down into this vat of mercury. Okay. And what's going to happen is I've got a pressure, two pressures at work. It's going to read a couple different ways. I've got the pressure of the atmosphere. It's pushing down on this liquid. Consequently, liquid wants to move, so it's going to be pushing up on the column here. I've also got pressure that's being exerted from within, from the mercury itself being accelerated down. Okay? So these two are going to be pushing until this thing is equal, until the two pressures, the two forces are equal. Okay? And so wherever this thing lands, wherever it's at in this tube, it will reflect, measuring this, if we've got some kind of a gradient here, I can measure its height, whatever, then that will tell me, whatever level it's at, and whatever reading I get, that will tell me the pressure that's being pushed down on this thing, okay? On this barometer. It says here, if the liquid is water, the normal atmospheric pressure will support a column of water over 10 meters high. So, I mean, you can just, it'll just push it up. You need a huge, just think about how big 10 meters is, right? Yeah, very impractical. Which is rather inconvenient for making and reading a barometer. Because mercury is very dense, 13.6 times denser than water, a mercury barometer only needs to be 13.6 as tall as a water barometer, which is more useful. A standard atmospheric pressure of 1 atmosphere at sea level corresponds to a column of mercury that is about 760 millimeters high, right? How much is that in meters? Like 7.6, right? Yeah. Okay, so, just imagine I'm going to estimate about here. Okay. So, pressure of 1 atmosphere is equivalent to the pressure of, where'd it go? Where was I?
760 millimeters.
760 millimeters, thank you. Of mercury. Okay. The torr was originally intended to be a unit equal to 1 millimeter of mercury, but it no longer corresponds to that exactly. Pressure exerted by a fluid due to gravity is known as hydrostatic pressure. We can calculate pressure given the following: pressure equals height times density times acceleration due to gravity. That's our formula. I'm going to write it out. Pressure equals height of the column supported times the pressure, or I'm sorry, not the pressure, times the density of the fluid times the acceleration due to gravity. And we'll do some calculations that break these, and we'll be given some variables and not others. All right. So the problem it wants you to be able to do here. To show the calculation which supports the claim that 1 atmosphere of pressure at sea level corresponds to the pressure exerted by a column of mercury of 760 millimeters. And to do this, it tells us that the density of mercury, our P, is 13.6 grams per centimeter cubed. Okay, so taking our formula, pressure equals 1 atmosphere. Okay, yeah. Our height is 760 millimeters, right? And our density is 13.6 grams per centimeter cubed, right? And then our acceleration due to gravity is
9.8.
9.8 meters per second squared, right? Okay. All right. Well, let's take a look at our units here. We've got meters, we've got to deal with, we've got seconds, we've got to deal with, we have a conversion that'll help deal with those seconds, right? What is that?
The Newton.
Yeah, so give me those numbers.
It's 1 Newton for meter squared is 1 kilogram per second cubed.
1 Newton meter squared, or 1 Newton meter squared. Newton per meter squared equals 1 kilogram squared, right? Okay. Oh my goodness. So here's what it wants us to do. It wants us to go, hey, our pressure equals. We're going to go from millimeters into meters. So I'm going to go 760 millimeters times 1 meter over 1,000 millimeters. That'll get us into meters, right? And now we're going to deal with our pressure. Right, we've got 13.6 grams per centimeter cubed. We're going to get from grams to kilograms. So we'll do that by going 1 kilogram over 1,000 grams. And we're going to get from our centimeter cubed into our meters cubed. And to do that, we've got to cube 100 centimeters, right? And that's equivalent to 1 meter cubed. What is 100 cubed?
100 cubed?
Yeah.
It's 80. Yes, I think.
That seem right?
Yeah.
Okay. Okay. So this will get us into kilograms per meter cubed. And then, if I multiply that by my 9.81 meters per second squared, and I'm not sure is getting from the meters per second squared into the Newton meters. This is where my head is ready to pop earlier. Not functioning as we were talking about before. Let's go ahead and work these below. So we get 0.76 meters, 0.760 meters, right? Times, should be 13,600 kilograms per meter cubed, times 9.81 meters per second squared. And when I run all this out, it'll give me 1.01 times 10 to the 5th kilogram per meter second squared. Which kilogram meter per second squared, this is where it is, and this is why I kept, my brain wasn't working. Kilogram per meter per second squared is equivalent to 1.01 times 10 to the 5th Newton meters. Okay. And that is equivalent to 1.01 times 10 to the 5th Pascal. Which, if we go look at what an atmosphere is, we should get 1.01 times 10 to the 5th Pascal. My head froze over here on that one.
Yeah.
All right. Let's go on to calculating barometric pressure. I'm sorry, not barometric pressure. Using a manometer, which is a little easier. So this will get better. When we actually get into gas laws, it'll really get good. set and turn the arrow? It was crazy hot and now here.
Yeah.
I'm thankful. This feels weird. Okay. A manometer is a device similar to a barometer that can be used to measure the pressure of the gas trapped in a container. A closed-end manometer is a U-shaped tube with one closed arm, one arm that connects to the gas, to be measured, and a non-volatile liquid, usually mercury, that sits in between. So it looks like this. So I've got some sort of a gas in here, and that gas is ultimately trapped because I've got mercury in between, right? And this thing is open. So if these two levels are the same, what can I say about the pressure of the gas in the tube and the gas in the atmosphere? They're the same, right? However, if this is higher, then what will I say about it?
The pressure of the gas is higher.
Pressure of the gas is higher, and if it's lower, then the pressure of the atmosphere is lower. And so this is useful for measuring atmospheric pressure. Okay. So it says here, the pressure of a sample of gas is measured with a closed-end manometer, as shown to the right. The liquid in the manometer is mercury to determine the pressure of the gas. So here's what it's telling us. I've got this drawing right here. The difference between these two is 26.4 centimeters. Okay. All right. So it wants us to calculate this pressure in torrs, in pascals, and in bars. Okay? So we've got, in each case, 26.4 centimeters. Okay? So we need to look at our chart and find a way of getting from torrs to centimeters. Or from centimeters to torrs, right? Is there a step that would link torr to centimeter? What do you got?
At the millimeter of...
Get to millimeters. So I'm going to multiply this by 10 millimeters over 1 centimeter. And I multiply that by, it's conversion between millimeters and torr.
It's equals 1 to
1 to 1, right? So 1 torr over 1 millimeter. And so when I do this, it's just 26.4 times 10. What's that going to give me? 264 torr. Good. Okay, now I want to do this. I want to get it to Pascal.
760 torr.
760 torr equals
101,000 Pascal.
Okay, so I'm basically going to run the same calculations, 26.4 centimeters times 10 millimeters over 1 centimeter times 1 torr over 1 millimeter. And now, what's my next one?
760 torr under
760 torr.
and 101,325 Pascal.
325 Pascal. Okay, and am I wanting Pascal or kilopascal? I want Pascal. Okay, so we'll solve that.
35,197 per month.
So let's put our 197.1 in sig figs and we get 200. Okay. This is 200 Pascal. Okay, good. Now we want this in bars. So what's our relationship between bars and all of these?
1 bar is 100,000 Pascal.
Bar is 100,000 Pascal. So I can take this same number here, right?
Yeah.
I can go 35 to 100 Pascal. And what am I doing with it?
No bar, so 1 bar
1 bar.
is 100,000 Pascal.
How many?
100,000.
100,000. Okay. So I go ahead and I do that. Should get what? 0.35?
Yeah, 0.35.
352. Okay. Easy enough. Told you that would be better. All right. Let's go ahead and we'll do one more sample problem off of this before we go into some of these others. So it's the same problem, but this time the difference in the column is 6 inches. Okay, so we're going from 6 inches to torr and Pascal and bar. Okay. So first thing I got to do is take 6 inches and do what?
Transform into centimeters.
So 2.54 centimeters per 1 inch. Okay. Now I'm going to go from centimeters. I'm going to go 1 centimeter to 10 millimeters. Right. And now I go to do my torr. It's just 1 millimeter equals 1 torr. Okay. So that's easy. Let's go ahead and run that. Yep. 152.4. And now we're going to go ahead and we're going to do it to pascals. To go from torr to Pascal, right, we needed to use this conversion here. So I can go 152.4 torr times 101,325 Pascal over 760 torr. Okay. All right. What'd you get there?
20,318.3.
Okay, and now C. I just want 20,000 here. And now for C, we're going to convert that to bars. And so to do that, I just divide it by 100,000. Right. So I'm going to go 20,000 divided by, and that's in, getting my units here. 20,000 pascals over 100,000 bars.
100,000 Pascal.
I have that backwards now.
Yeah, 1 bar is 100,000 Pascal.
Bars 100,000 pascal. Okay. So go ahead and run that. 0.2. Okay. All right. Pressure of a sample of gas is measured at sea level with an open-ended manometer, as shown to the right. Determine the pressure of the gas in, we just do this one. No, we did not, okay. It's essentially more the same, but I'm gonna trust it. We should. Pressure of a sample of gas is measured at sea level with an open-ended mercury manometer, as shown at the right. So the drawing that we have is this one. This is 4.63 inches. Now, sorry, I just looked at the wrong drawing. Wrong drawing. Okay. Difference here is 13.7 centimeters. Okay. And it would like us to calculate it in millimeters of mercury and in atmospheres. And in kilopascals. Okay. Erase over here. Okay, so how do I convert 13.7 centimeters of this into millimeters of this?
Why would they?
Oh, my eyes. Our others were for closed-ended. This one's for an open-ended. So we've got this pressure plus pressure of the atmosphere, okay? And what we're trying to figure out is the pressure of this gas. So it's not as straightforward as it would look. So what we have to do, I gotta start bringing my glasses, I can't read. We've got 13.7 centimeters, right, times 10 millimeter over 1 centimeter, right? Now we have to add the pressure coming from the atmosphere, 760 millimeters of mercury, right? And so now when I do this, I get 137 millimeters plus 760 millimeters, and that's going to give me 897 millimeters. Okay. Now, if I want this in atmospheres, I can take my 897 millimeters, right? And how do I convert from atmospheres to millimeters? I go look at my chart. and I know that a millimeter is equal to a torr, and I know that an atmosphere is equal to 760 torr, right? So I can go in reverse, right? I can go times 1 millimeter Hg over 1 torr, right? And then I can multiply 760 torr over 1 atmosphere. That would give me my answer in atmosphere. So I basically have 897 divided by 760. That should be 1 point something something, and it is going to be 1.18 atmosphere. Okay. Now to get to kilopascal, I know the first thing I've got to do is get to Pascal. I probably have a conversion between Pascal and atmospheres somewhere, or something close, right? So what is that?
1 atmosphere is
101,325. So I'm going to take my 1.18 atmospheres, right? And I'm going to multiply that by 101,325 Pascal over 1 atmosphere. Then I'm going to multiply my, what am I wanting here? Kilopascals. So I need 1,000 pascals over 1 pascal. Okay. So this is as simple as 1.18 times 101.325, which will give me what?
119.56.
What do you get?
119.56.
That's not what they're giving. Let me see. What do you say? Give me your number again.
119.56.
1.56. Yeah. Oh, okay. For whatever reason, they're choosing to be in scientific notation with us, and it's just a little odd. And then they round it. So we're getting 119, right? Which would then convert to 120. They're putting it as 1.2 times 10 to the second, which is the same. All right. Let's do one more of these, open-ended, because these are ones we do have to be able to do. And I think we finally get into our gas laws. Pressure of a sample of gas is measured at sea level with an open-end mercury manometer, as shown to the right. Okay, in this case, it's going to look like this. Is 4.63 inches. So it would like me to give these answers in millimeters of mercury, in atmospheres, and in kilopascal, right? So the last one, we had more pressure here, right, than the atmosphere. And so we added the atmosphere plus this pressure. In this case, it's going higher, right? So we've got to subtract that amount. so we'll bear that in mind. All right, this is 4.63 inches. So I got to go 4.63 inches and convert it, multiply by 2.54 centimeters per 1 inch, right? And then I've got to go, of course, 1 centimeter equals 10 millimeters, right? And then I'm trying to get, oh, I'm there, okay. And now,
760 minus, what do you
I
get?
think it's 760 minus this. Let's run it both ways and be sure. What do we get with this? We get 4.63 times 2.54 times 10.
They rounded up to 118.
Yeah, it's going to be 760 minus this. Y'all are welcome to come in if you like. So we got to set this back up slightly different. We're going to go 760 millimeters. Minus that, right? Okay. So that's my A. And this puts me at 642. Okay. Now that I've got that though, I don't have to fuss with it anymore. I'm just going to convert that to atmospheres and then to kilopascals. So to do that, I'm going to go from 642 millimeters of mercury, and I need to get to atmospheres, right? So I can go from millimeters to torr, right? What's that conversion?
So 1 millimeter is 1
Okay. And now I can get from torr to atmosphere. What is that?
1 divided by 760.
Okay. So when I do this, I've got 642 divided by 760, and it's going to be like, what, 0.8, 0.9, something like that. They are... I think I did it backwards. I think I reversed my reverse. I don't know what I did, but I did. This is plus, which is everything else we've done. Let's do this again. What did this number come out to? Run it one more time. 760.
He said 60 plus.
Oh, I'm sorry. Let's not 760. Let's ignore the 760 for a minute. Let's go 4.63 times 2.54 times 10 equals
117.6.
Wait, what? I did 137. How are we getting something very different? Because I am doing the wrong problem. What did we have written up here originally? 644? 642?
Yeah. It was right, it was...
He was right.
Okay. Okay.
This is what I'm looking at. So, you just take your eyes off of something and you put it on the wrong thing.
Oh, it's good.
And you're just...
If you want to to go to ATM.
Let's do this again. Oh my goodness. Okay, our 642 millimeters of mercury. Now I've erased everything else we did. We were going from millimeters to torr, right? And so that's 1 torr over 1 millimeter, and now we're going, pardon?
We're going to ATM.
What was it, 7?
It's 1 over 7.
1 over 760?
Yeah.
Torr for 1 atmosphere. But of course, we needed to subtract 700. No, we did not, because we already did that. Okay, great. All right, and this math came out to 0.845?
Yeah.
Perfect. I shouldn't even do my own math, I should just look at their answers. We'd be a lot better off. C. Okay, so now we're going to kilopascal, right? So kPa. All right, so I had 0.845 atmospheres. This is millimeters of mercury. Okay, 0.845 atmospheres, and I need to get to pascals so that I can get to kilopascals. What do I convert it to?
You multiply by 101,325. 1 ATM is 100,125 Pascal.
100 and
101,325.
101, column of 325 pascal is 1 atmosphere. Okay, and now I need to convert that to 100,000. I'm sorry, to 1,000 pascal over 1 kilopascal, which will let me go 0.845 times 101.325, and what do you get?
85.62.
85.62 kilopascals. And I'm going to be so glad to be done with manometers and barometers and on to something else. How much time do we have? Oh, not much.
Not much.
Not much. But at least we're done with this. Just took us the whole day. We're on to gas laws after this, and these make sense. These are much easier. You've had it all before? Good. I don't ever remember having to do all this. Not in high school, not in college, not in grad school. Gas laws, yes.
Yeah, I remember more of the gas law. I remember the columns, but not doing many problems about it.
All right. You don't care about any of those. We'll stop here for today. This will be a good stop point. We'll pick up with our gas laws next time with a clean slate, hopefully enough sleep. I'm not going to be here Wednesday. You have nothing on Wednesday. Next class will be on Monday. We will have gas laws. We'll have a test on the Wednesday. Okay?
The Wednesday, then you're not going to be.
No. Okay. So here's today. This is Monday.
Yeah, today's Monday. Oh, this Wednesday, you know.
Yeah. So Wednesday, no class.
Okay, and then gas law, test.
Then the next Monday, gas law.
And then test.
And then the following Wednesday, test.
Got it.
And then back to gas laws.
All right.
Which is good stuff. Okay. Well, that's all I got.